I'm Megan Hahn.
I'm Maria.
I'm Tomas.
I'm Jahan.
I'm Ganli.
I'm Samuel Hood.
Again.
Okay, so we're group 5, we're a vegetation group, and our project was classifying vegetation in Nebraska using Landsat remote sensing data. Oh. All right. So just before we get into the details of our project, we want to go over some background. So first of all, what is land cover? Land cover is just basically the surface cover. And so what we mean by that is just like the type of vegetation, so like maybe corn, soybeans, or it could be water. So it's just like the type of what is the surface of the ground. Also, we want to go over what remote sensing is, and it's the scans of the Earth by the satellite. So these satellites are able to like get like reflectance values, and it uses these values to quantify a metric of measuring how much chlorophyll a type of land cover has, and because of that, we're able to like distinguish between types of land covers. And we're interested in the knowledge of land cover because vegetation affects climate, and climate affects vegetation. So what we mean by this is, for example, if you have, if you consider an area that has like moderate to high temperatures and it has an abundant amount of rainfall, typically you will see a lot of plants in that area, right? Also, land cover can be an important input into models. So there's various climate models out there that use land cover knowledge. So they can't run without knowing what types of land covers there are. And then also we're interested in identifying changes in land. So this helps us understand like agricultural practices and deforestation. So for example, if you consider like how bodies of water change over time, and we know how useful water is as a resource, we're interested in seeing like where water would be located at a certain spot in time. So, oh my. How do I, is it page? Okay, so here's some of the available data that we have. So like before this, the way that we were quantifying this, these reflectance values was using the Enhanced Vegetation Index. And then other data that we have available is dates corresponding to when this value was calculated. We have like the land cover type of each location, and we have the temperature over the region for each day. We have the X and Y coordinates for each location, and we have the longitude and latitude coordinates for each location. So just to give you an example of what this data looks like, we can look at a type of vegetation. So for example, let's look at soybeans. And we see this is plotted against time. And as we see as time goes on, there's a certain window where the EVI drastically increases. So we can see that's where like the soybeans are actually like growing. And then that's likewise for corn. And then for here, the land, we have a satellite image pretty much. So this is EVI, and you could tell by the colors of the metric that it uses, like what is this certain type of like EVI being there. So like for example, like this is really green, so it has like a lower EVI, and then the EVI increases based off the color.
Okay, so the main question that we were trying to answer was is it possible to use remote sensing data to classify land cover in a specific area? So we basically accomplished this by training various models using 2008 data from this small piece of land in Nebraska. And yeah, so that's an overview of what we were going to do. So our plan for the week was to start with exploratory data analysis. So we looked at the EVI values for different parts of the region, and also for each specific type of vegetation that was in the data. And then parallel with that, we also researched different models that we could use, such as logistic regression models, multinomial regression models, and random forest models. And so we kind of did that at the same time, and then we came up with a list of features that we could implement into the models together. And then a good portion of the week was spent implementing these models in R using the random forest packages. We didn't end up using NNet. And then we tested the program against a training data set and a test data set, and then a 2010 data set. And our goal was to achieve 85% classification in the area that we were studying. So one of the first things that we did was look at different types of features. So I'm just going to go through a couple of features that we paid attention to. So the graphs that you see up here are EVI values basically EVI values with respect to time for each different type of vegetation that was present in the data set. So for corn, so for water, you can see that there's a great difference between like the way the graph looks, and that's because water doesn't really have much of an EVI value or like change in EVI value. It stays pretty constant throughout the year. And then if you pay attention to the numbers and like the peak of the EVI values, you can tell that those are also different. So we kind of looked at all these factors to figure out how we could distinguish between what was corn and what was a deciduous forest and things like that. So what we just looked at was basically the spring green-up phase for each vegetation type, and you could tell that they were pretty different, so that was one of our good features that we used as a covariate in our model. Another really good feature that we used was the longitude and the latitude, which is the location of each thing that we looked at. And these are also different. They're not all labeled, but you can tell that we mostly struggled with distinguishing between deciduous forests and grassland herbs because they're so similar in terms of their location and their values in general. And then this is open water. You could tell it's drastically different from everything else in the longitude and latitude values. So it was really easy to distinguish between water and everything else. And then this is our minimum EVI value, and this is probably one of our least used features in our model because there's not much of a difference between most of the different types of vegetation that we looked at, other than open water. And then this is just a table of all of the features that we considered when we were trying to fit our model. And we figured out, we were able to tell which features were more important based on the importance values that we discovered through our random forest model.
So the first model we used was called a logistic regression. And a logistic regression is basically a generalized linear model, and it has a Bernoulli random component and a Logit link function, which is demonstrated with the log p over 1 minus p. And since it's Bernoulli distributed, we have a binary outcome. And here the outcome that we're looking for is open water and just no water. And the importance of this is, as Sam was saying before, to see how bodies of water change over time. So we can use this for 2010 data to see if there's any shifts. And basically in this model, out of all the features listed before, we ended up just using one feature and got a pretty good prediction out of it. And multinomial logistic regression is an extension of the logistic regression from the slide before. And also, before I get into this model, the next two models you'll see, we will be classifying the 7 land groups, as compared to before we were only classifying 2 groups. And here, what we did was we fit a multinomial logistic regression, and then in our model, we use all the features in the table, and then we use the AIC values and backward and forward selection to select those features. And out of all the features, we use 13 features. And some advantage with this is you can do more than two categories, and it's kind of easier to understand than random forest. But there's a big chance of overfitting, and it uses linear prediction. And basically, going back to overfitting is when the model works really well on the test data, on the training data set, but on the test data, it doesn't have a good classification rate.
So in the random forest model is a machine learning algorithm that uses decision trees to categorize all the land parts based on our features. Right, so the random forest model is based a lot in the tree bagging, and it differs only in the fact that each vertex splits into another random subtree at a random, like they choose a random feature, which would be one of our vertex or our nodes, depends on how you learn it. And an advantage for the decision forest is that it avoids overfitting the data. If we use only one tree, it would overfit our data. So, like in the image we have here, we can see like it's just a combination of many trees that are randomized. But a disadvantage is that it's computationally expensive when you're trying to get it more accurate. To achieve more accuracy, you would need more trees, and it would take a lot more time to compute it. Our random forest, the procedure is that classification trees. For each tree, we take a bootstrap sample of the training data, meaning is with replacement, and we train the classification tree on the sample data, where each step of the tree is a random subset with n features. So every time we take a random subset, like I said before. And in classification, it also differs from the tree bagging in the way that you take the majority vote of the classification trees, which means of all those random subtrees we took, the one that has the most nodes in common, it means that it's a majority vote. If 50% of the nodes that were chosen is from one, or we'll take that. And we also decided to perform different, we tried to perform incremental experiments with the random trees. So we would change them, and from our data we would either split them into groups according to the type of vegetation they were, or by the sample size they had. So on the right side we see the one that is separated by agriculture, natural vegetation, and others, meaning the developed areas and water. And in the left side, they are all basically the same sample size, around 1,300 points.
So yeah, in order for us to actually verify which model is better, we use k-fold cross-validation. The detail is told by the other group, but I think basically the same idea is used here to verify like which model is the best, and we did k-fold cross-validation here. So after some training, we discovered these error rates and the error rates using k-fold validation. The error rate we use is by randomly just split the training data and the test data. And we can see that logistic regression does the best because it only splits the water part of the map with the non-water part, so it's very good. And because of that, we didn't use the cross-validation to verify its accuracy. But for the other three different models, we think it's the best to use random forest in order for us to classify the land cover type. And I think the interesting thing here is that we use three different kinds of random forest. The first kind of random forest is the direct application of this already studied algorithm. Basically, we put in the entire data set and train using the features that we discovered. But for the next two random kind of forest, basically what we did is we split the data sets into different categories, and we try to separate random forests at each step, at each level of the data. So if we separate the data set into like the vegetation, the water, and the developed different kind of the data, we trained it, and using two different kind of different level of random forests, and we obtained a quite nice result. As predicted by the traditional kind of random forest algorithm. And if we classify the sample size of the data, or of the similar sample size data together into the same level, we can obtain an even better result. as seen in the tenfold cross-validation. For now, we can't really see the advantage of this multi-level random forest approach, but later when we are using the models to predict the data in the future, we can actually see the advantage of this compared to the traditional random forest algorithm. So we are gonna
2 minutes.
We have one small thing,
Yeah,
so
that's
the
a
error
typo
rate,
in the
yeah.
logistic regression.
So it's a 0.9.
It's supposed to be
That's
0.9, not a 99.1.
That's our correct concentration.
Yeah, so we can see here is the confusion matrix, and basically each row and each column corresponds to a category, and only the diagonal shows like the correct prediction. And we can see most of the data have their have correctly been classified. Next. Now we are using the 2008 data to train, and this is the original land cover data that's collected manually. But using the remote sensing data, we get this result as predicted, and we can see there are some misclassifications, but we can see the overall result is quite okay. Next, the more interesting thing is that we used the data in 2008 to train the model, but we try to use that to predict the 2010 data. This is actual land cover, and here is the data predicted using the traditional one-level kind of random forest model. And we can see the accuracy is lower, but we can see basically the big areas are covered. The interesting thing about 2010 data is that in 2008, the area that plants soybean and the area that plants like corn is completely different from the area in 2010. So it's one of the worst kind of situation in which we can predict. So we want to try to see how good it is.
Okay, time to wrap up. All right.
Yeah.
So our conclusions were random forest produces the best results, and the multi-layer one was actually less effective than the regular single-layer one. And logistic regression model works well when you have two very distinct types of vegetation.
So a problem that we had was there was a lot of missing data in the Landsat data we used, and it was reported every 16 days. So a way we could make up for that is also introduce the MODIS data, which is used more often, which is recorded more often. And we could also apply this to a larger data set because our sample plot in Nebraska was pretty small.
And we can also use different types of methods to analyze data, like spectroclustering using PCA. Shout out to our postdoc.
Thank you, everybody.
Yeah, and everyone.
All right. Okay. Nice job being agile there at the end when I was being mean and nasty. All right. Questions? Yeah?
Since we both are something similar, so did you guys consider like interaction terms for your, like when you were initially exploring your data set?
Oh, interactions between the different covariates.
Yeah.
I think in some like with the features, we in a way we did because we would be comparing to like.
Because you have like water and you have like.
I don't think we put like the features interacting together in the models. We kind of just did them singly. Yeah. So
So could that be like considered for future? And I'm just curious, like.
We haven't done it, so I'm not sure, but I don't think it would increase our classification rate by a significant percentage. That would be my guess. That
For the linear regression model?
I don't think it would increase it by that much.
And did you also have like any uncertainty there that you, I think you mentioned water, right?
The water classification was with the logistic regression was pretty good. It was like an error rate of 0.9. It was just with the multinomial logistic regression, we had an error rate of around 33% because it was using like it was linearly classifying it, and not all the features are related that way. So, and then with the random forest, since it uses a different algorithm, we got much higher classification.
Thank you.
Anything else? So I had a question for you. So if you think about bringing in the MODIS data product, how would you combine those two? Because now you have two different things.
So the Landsat data, so the higher resolution picture that we saw, sometimes there's gaps in that information, and because MODIS is done over like more, is done quicker, so it's like more of like a low resolution pic. So we were trying to use that information, probably fill in the data for the Landsat, because as of right now we can only like predict on where we have information from. So just trying to fill in those missing holes.
I think at the beginning of the week, when we were thinking about doing both problems, like we were brainstorming using like new Gaussian processes, because we want to predict, they're like the locations are related, so we wanted to like predict based on that and kind of combine that to get a better data set. So that was our idea, but we didn't get into it. We were just kind of talking about different models to use.
Anything else? All right, let's